Ever used printf in C and thought you knew how it works? We're uncovering the hidden precision rules behind printf, the differences between %d and %f, and one subtle behavior that every professional C developer must understand: automatic type promotion. If you've ever printed a number and wondered why it looks a little off, this lesson will fix that forever. Let's start with the basics. When we write int n equals 32 printf, the value is %d\n. We're telling the compiler, hey, this value is an integer. Use %d to display it. And the output, as expected, is the value is 32. So far, simple. But here's where most beginners stop. Printf can do far more than just print integers. Now, what if we use a decimal value? Float n equals 32.654, printf. The value is %f\n, the result. The value is 32.654000. Notice something? Even though we declared n as a float, %f still works perfectly. Why? Because when we pass arguments to printf, C automatically promotes floats to doubles. This means every time you print a float, you're actually dealing with a double under the hood. That's not an accident. It's by design, and it's called default argument promotion. Let's break that down. A float takes up 4 bytes of memory. A double takes up 8 bytes, twice as much precision. When printf runs, it doesn't know the variable's original type. It relies entirely on the format specifier, %f, %d, %s, and so on, to interpret what's passed in. So if you mismatch them, like using %d for a float, you won't just get the wrong number. You'll get garbage output. That's why type discipline in printf is non-negotiable. Want to print fewer decimal places? You can control that directly with format specifiers. For example, printf value %.2f\n. This limits the output to 2 decimal places, giving you value 32.65. Every professional C programmer uses this trick to control output precision, especially when formatting data for reports, logs, or user interfaces. Here's the mindset shift that separates beginners from experts. When you call printf, you're not just printing text, you're creating a format contract between your code and the compiler. Each specifier, %d, %f, %s, tells the compiler how to read the memory of what you're printing. Use the wrong one, and that contract breaks. That's when weird numbers, truncated output, or crashes start to appear. Let's recap the essentials. 1. Use %d for integers, values without decimals. 2. Use %f for floats and doubles, anything with fractional parts. 3. Remember asterisk floats are automatically promoted to doubles when passed to printf. Master these, and you'll never misprint a value again. That's how you take control of your output in C: precision, clarity, and consistency. If this gave you that aha moment about how printf really works, don't just move on, apply it. Your compiler already knows the rules. Now you do too. Ever wondered why typing printf %c 65 prints A? Thinking face, this is not just another syntax walkthrough, but a breakdown of how printf actually interprets your data under the hood in C. You'll not only use format specifiers confidently, you'll understand what's really happening in memory every time you print something. Let's start with the basics. In C, %c is the format specifier that tells printf, hey, this value is a character. Example, char n equals A. Printf, the character is %c \n. Output, the character is A. Simple enough, right? But here's where it gets interesting. Try this instead. Int n equals 65. Printf, the character is %c \n. Output, still A. Why? Because in C, a char is not truly distinct from an integer at the hardware level. Characters in C are just small integers, specifically integers that represent ASCII codes. So A is really the number 65, B is 66, and so on. When you print with %c, C simply takes the integer value and interprets it as an ASCII character. That's why an int with value 65 and a char with value A behave identically here. Key takeaway: char is just an 8-bit integer with a specific meaning attached, a human-readable symbol mapped to a number. You've already seen %d, %f, and %c, but C gives us a full toolbox of format specifiers. Here are some that every serious programmer should know. %u, prints an unsigned integer. No negative values, just raw binary interpreted as positive numbers. %x prints an unsigned integer in hexadecimal, using lowercase letters, a to f, %x, same as %x but uppercase a to f. %o prints the number in octal, base 8. These are crucial when debugging, inspecting memory, or working close to hardware, because you're often interpreting the same bytes in different numeric systems. For example, int x equals 255. Printf, %d %u %x %x%o \n. xxxxx. Output, 255 ff 377. You just saw decimal, unsigned, hexadecimal, and octal, all from one integer value. Now here's a quick gotcha. If % is reserved for format specifiers, how do you literally print a % symbol on screen? You've got two options. Use %c and pass % as an argument. Printf, %c, %. Or simply use %% inside your format string. Printf, CPU usage, 85% %\n. Output, CPU usage, 85%. Elegant and clean. That's how you display percentages properly in C. Here's the professional mindset. When you use printf, think in terms of data interpretation, not just printing. %deb interprets data as a signed integer. %u interprets it as unsigned. %cs interprets it as ASCII character. %x interprets it as hexadecimal representation. The data doesn't change, only how you view it does. Understanding this mental model makes debugging and system-level programming far easier. So here's your quick summary. %c prints a character. C treats char as a tiny integer, ASCII encoded. Use %u, %x, %x, and %o for unsigned, hex, and octal outputs. To print %, type %. Once you understand why these specifiers exist, you stop memorizing and start mastering the fundamentals of how C talks to the machine. Have you ever wondered how to make your C programs print output exactly the way you want? Perfectly aligned, formatted, and clean? Most beginners only scratch the surface of printf. We're going deep into formatting precision, special characters, and the hidden symbols between % and your format specifier that give you total control. Let's start with the basics. When you write something like printf %dx, you're telling C, print the value of x as a decimal integer. But that %d isn't just a placeholder. It's the tip of the iceberg. Between the % and the format character, you can actually insert modifiers, special codes that control width, precision, alignment, padding, and sign display. For example, %5d prints your number in a field that's 5 characters wide. %05d pads it with zeros. %-5d left aligns it. %+d always shows the sign, even for positive numbers. These tiny details make your console output look intentional, not accidental. Here's a quick cheat sheet of what you can put between % and your format specifier. Flags control alignment and signs. Examples. For left alignment plus to always show a sign 0 for zero padding hashtag for alternate output forms, like adding 0x for hex values. Width, minimum number of characters to display. Precision, for floating point numbers, it's the number of digits after the decimal. For strings, it's the maximum characters to print. Length modifiers specify variable size, L, LL, H, etc., so the format matches your data type exactly. In short, % flags, width, .precision, length specifier. Once you understand this structure, you can design your program's output as precisely as you design your algorithms. Now let's talk about something even more subtle, reserved characters like \n or \\. When you type \n, it's not two separate symbols, it's one escape sequence. It tells the compiler, insert a new line here. Example, printf, here's a new line, \n. Output, here's a new line. You can place it anywhere. Printf, here's a \n new line, \n. Output, here's a new line. Other common escape sequences you'll use all the time. \t tab space \, double quote inside strings \, prints one \. And just like % prints a single %, \/ prints a single \. These aren't random tricks, they're part of how text is encoded in C. Understanding them is key to writing output that's both readable and well-structured. Formatting might sound cosmetic, but it's not. In technical output, clean formatting improves debugging clarity, report generation, and user readability. A developer who knows how to control printf is one who can make data talk cleanly, clearly, and professionally. Go explore every possible formatting option between % and your format character. Practice with different escape sequences until they're second nature. Once you do, your console output won't just show data, it'll communicate information. If you found this breakdown valuable, don't just stop here. The deeper you go into how C handles data presentation, the stronger your foundation becomes. This is where code stops being messy text and starts becoming a language of precision. Ever wondered why your C program gives a result you didn't expect, even though your math looked right? It all comes down to one powerful concept: how functions, statements, and operator precedents actually work under the hood. In this lesson, we'll break it down step by step, clear, precise, and practical, so you write cleaner, smarter code that behaves exactly as you expect. Let's start simple. In C, everything inside the curly braces of main is a statement and instruction the computer executes, line by line. Here's an example: void main. Int a equals 5, int b printf, answer is %d\n, a equals 6, b equals a. Each line or statement ends with a semicolon. Statements do something: declare, assign, or output. And in this example, we meet a new kind of assignment, b equals a. Instead of assigning from a constant like 5, we are assigning from another variable. That's your first taste of expressions in action. An expression is simply the right-hand side of an assignment. For example, in b equals a plus 2, the expression a plus 2 is evaluated first, then its result is stored in b. But expressions can get as simple or as complex as you want. That's where operators come in. Let's see them in action. A equals b plus 1. This is addition a equals b minus c. This is subtraction a equals 4 asterisk c. This is multiplication a equals b slash 3. This is division. Each operator combines smaller expressions into something more powerful. And these 4, plus, dash, asterisk, forward slash, are the backbone of mathematical logic in every C program. Now here's where many beginners, and even pros, get tripped up: precedence. When your code has more than one operator, C needs to know which one to do first. That's where precedence comes in, the hierarchy that decides the order of evaluation. Here's the rule of thumb: multiplication, asterisk, and division, forward slash, come before addition, plus, and subtraction, dash. So this line, a equals b plus c slash d asterisk e, is evaluated as if you wrote a equals b plus c slash d asterisk e. It's not left to chance, it's the compiler following strict rules. But when operators share the same precedence, like plus and dash, they're handled left to right. That's called associativity. You can take control. Parentheses are your best friend when clarity matters. They override normal precedence, forcing C to evaluate what's inside first. For example, a equals b plus c forward slash d asterisk e. Now there's zero ambiguity. Even the compiler knows exactly what you intend. You can even nest parentheses like this: a equals b plus c forward slash d asterisk e. Each set adds precision and readability, crucial for debugging or complex calculations. So here's the takeaway. 1. Use clear statements. Each should do one specific thing. 2. Understand expressions. The right-hand side isn't just math, it's logic in motion. 3. Know your operators. Order matters, both for performance and correctness. 4. Use parentheses to control complexity. Never assume the compiler reads your mind. The best C programmers don't just write code that runs, they write code that reads like logic. That's the difference between debugging in minutes or hours. Master these fundamentals, and you'll never be surprised by a compiler again. Next, we'll go deeper into user-defined functions and how to make your programs modular, reusable, and powerful. Ever wondered how complex programs stay organized, efficient, and error-free? It all comes down to one concept: functions. Here, we're breaking down how functions make your C programs simpler, smarter, and more powerful. What exactly is a function? Think of a function as a named sequence of instructions, a reusable mini-program that performs one clear task. You've already seen a couple: main, the entry point of your program, and printf, which outputs text to your screen. Functions are like shortcuts. Instead of rewriting the same block of code, you give it a name, reuse it anywhere, and instantly make your program cleaner and easier to maintain. So instead of managing hundreds of lines of repetitive logic, functions let you group related code into logical, reusable components. Why functions matter? They simplify complex logic into readable chunks. They reduce repetition, keeping your codebase small. And they increase reliability, because one tested function can be reused across multiple parts of your program. The result? Cleaner architecture, fewer bugs, and faster debugging, the holy trinity of good programming. Now, you don't have to reinvent the wheel. C comes with a massive toolbox of predefined functions, known as C libraries. Need to do math, string operations, or file handling? There's probably a library for that. By tapping into these, you save hours of work, because someone's already written, optimized, and tested that code for you. Let's take a look at one in action. Example, the SQRT function. Say you want the square root of a number. Instead of writing your own algorithm, you can use C's mathematical library function, SQRT. Here's how it looks. Hashtag include math.h void main. A equals SQRT for 0. SQRT takes one argument, a number of type double, and returns the square root of that number. So SQRT 4.0 gives you 2.0. Functions like SQRT are not magic, they're just ready-made tools built into the language, and you simply plug them in. But here's a crucial question. How does the compiler even know that SQRT exists or what kind of data it expects? That's where function prototypes come in. When you include the line hashtag include math.h, you're not adding the actual function code. You're adding a prototype, a declaration that tells the compiler. There's a function named SQRT that takes a double and returns a double. In plain English, the compiler now knows exactly how to call it and what kind of value to expect back. Here's what that prototype looks like inside the library, double SQRT, double N. It's basically a contract, defining the input and the output types, so your program and the library can talk to each other correctly. Without prototypes, your compiler would be guessing, and that's a fast track to bugs or crashes. With them, every function call is type-safe, predictable, and easy to debug. So the moment you write or use a function, always make sure there's a matching prototype, either in your code or in a library header file. To recap, asterisk functions make your code modular. Asterisk libraries give you pre-tested functionality. Asterisk and prototypes keep your compiler and your sanity in check. In the next session, we'll go beyond using functions and start creating our own with parameters and return values that make your programs truly dynamic. Have you ever looked at your C code and thought, there has to be a cleaner way to do this? Well, you're right, and that cleaner way starts with functions. We'll break down exactly how to create, use, and reuse your own functions in C, step by step, and by the end, you'll understand how professional developers keep their code elegant, modular, and error-free. Let's start with the big picture. Functions are like building blocks in your program. Each block does one job, clearly and reliably. Instead of repeating the same code over and over, we define a function once, and call it whenever we need that task done. That means fewer bugs, easier debugging, and a program that actually makes sense when you read it 6 months later. Every C program starts with one special function, main. Think of it as your program's entry gate, the very first line the computer runs. Example, hashtag includes stio.h void main. Printf, hello world \n. Here, main calls another function, printf, which is predefined in C's standard library. So even before writing your own, you've already been using functions. Now let's create a simple one ourselves. Say we want a function that just prints a blank line. We'll call it one_line. Here's how it looks, void one_line void, printf \n. Let's break that down. Void before the name means it doesn't return any value. Void inside the parentheses means it doesn't take any inputs. Inside the braces, we define exactly what it does. In this case, print a new line. This structure, define, describe, and do, is the core pattern of every function in C. Now that we've written it, we can call one_line anywhere in our program, just like printf. Example, C# includes stio.h void one_line void, printf \n, void main void one_line. That single call inserts a blank line in your output. And here's the beauty. If we want 3 blank lines, we don't rewrite the code. We just call the function 3 times. But why stop there? We can build new functions out of existing ones. This is how modular design works. Let's create a new function called 3_lines that calls 1_line 3 times, void 3_lines void, 1_line, 1_line, 1_line. Now our main function becomes even simpler, void main void 3_lines. Notice what's happening? We've abstracted away repetition. If we ever decide to change how a line break works, we only modify it in one place, inside 1_line. This is how professionals make code scalable and easy to maintain. Let's recap the principles you've just applied, because these are the foundation of every great software system. 1. Encapsulation. Each function does one clear job. 2. Reusability. Write once, use anywhere. 3. Abstraction. Hide details, expose clarity. 4. Maintainability. One change fixes everything that depends on it. That's not just good C programming. That's good software engineering. So next time you catch yourself copying code, stop and turn it into a function instead. It's the simplest upgrade that separates beginner coders from true developers. Before your code can think, it needs to communicate. And that communication happens through functions, the beating heart of every program. But here's a secret most beginners miss. It's not just about writing a function. It's about how data moves in and out of it. We'll break down arguments and parameters, the invisible bridge between your main program and your logic. You'll understand how professional-grade functions are built to handle inputs, outputs, and efficient data flow. Let's decode how data actually travels through your code. Think of a function like a machine. You feed it inputs, it does some work, and then optionally gives you an output. Inside the function's blueprint. That's your definition. We describe what kind of input this machine expects. Those are called parameters. But when you actually use the function, when the machine runs, the real data you send in are called arguments. So parameters are placeholders, like empty input slots in a machine design. Arguments are the actual data you plug in when the program runs. It's the difference between defining a recipe and cooking it with real ingredients. Let's see it in action. Here's a simple C function that calculates the square of the difference between two numbers, double_diff, double A, double B, double diff equals a minus B, return diff times diff. What's happening here? The parameters are A and B. They're just local variables declared inside the function definition. When we call _diff 10, 6, those numbers 10 and 6 become the arguments. Inside the function, we compute the difference, a minus b, store it in diff, then return diff asterisk diff, the key takeaway. The parameter names are just placeholders. Each time you call the function, those names are replaced with new argument values at runtime. Every function can either return a result or simply perform an action. In this example, the return statement does two things. 1. It sends the result of the expression diff asterisk diff back to where the function was called. 2. It ends the function's execution immediately. Any code that appears after a return statement will never be executed, and we call that dead code. So whenever you design a function, think of return as the exit door of the function. Once you go through it, there's no coming back. Here's where a lot of beginners get tripped up. The input types and output types of a function are independent. Just because a function takes two doubles as inputs doesn't mean it has to return a double. You could easily write something like int my_function double n char x. Do something complex. Here, the inputs are a floating point number and a character, but the function returns an integer. This flexibility is what makes C so powerful. You can design functions that take in various types of data and produce whatever kind of result your logic demands. The key design principle, the function signature, defines a contract. What types go in and what type comes out. Keep that contract clean, consistent, and predictable. Let's summarize what we've learned. Parameters live in the function definition. They're the theoretical inputs. Arguments are the real data you send when calling the function. Return statements send results back and stop the function immediately. Input types and output types are fully independent. Use that freedom intentionally. Mastering these basics isn't just about writing cleaner code. It's about writing reusable, testable, and scalable logic. This is the foundation of every efficient program you'll ever write. In the next session, we'll explore scope and lifetime, how variables behave inside and outside of functions. But before you move on, remember this. Functions are more than code blocks. They're contracts of trust between different parts of your program. Write them thoughtfully, and your code will never let you down. Ever wondered why C and Java demand you declare every variable type, while Python just figures it out? The difference isn't just syntax. It's a core design principle that defines how your code behaves, how fast it runs, and how many bugs you'll catch before you even hit run. We're breaking down types and type conversion, the real reason programming languages think and behave so differently. Let's start with one simple truth. Every programming language has a system to handle types, whether you see it or not. In C, for example, you must declare the type of every variable, every parameter, and every return value before you even compile. That's what makes C statically typed. The compiler needs to know exactly what kind of data it's working with, long before your program runs. But there's more. C is also strongly typed. That means once a variable has a type, say an integer, you can't just treat it like a float or a string unless you explicitly convert it. The compiler won't let you cheat. This strictness is what gives C its precision and performance, but also its reputation for being unforgiving. So what's the opposite of that? In dynamically typed languages like Python or JavaScript, types are figured out at runtime. You can just write x equals 5 and the interpreter decides. That's an integer. Later, if you do x equals 5, it won't complain. It'll simply change the type. Static typing means the type is fixed at compile time. Dynamic typing means the type is discovered at execution time. Both have trade-offs. Static typing catches more bugs before you run the program. Dynamic typing lets you move fast and write less code, at the risk of runtime surprises. Now, let's talk about strength of typing, how strictly a language enforces its type rules. Strongly typed languages, like Java and Python, require explicit conversions. You can't mix types without telling the interpreter or compiler exactly what you want. But in weakly typed languages like Perl or VB Script, the rules are loose. You can literally take the string 12, add the integer 3, and get 123. And then treat that as the number 123. The language quietly does the conversions for you, even when it might not make sense. Flexible? Yes. Safe? Not always. Type conversion is where things get really interesting. There are two main kinds, implicit and explicit. Implicit conversion, also known as type coercion, happens automatically. The compiler or interpreter decides to convert one type to another behind the scenes. Here's a quick example from C, double invert, int n, return 1.0/n. When dividing 1.0 by n, the compiler automatically converts the integer n into a double. Because the operation involves a double, that's coercion, no manual effort required. But explicit conversion, or type casting, is when you tell the compiler exactly what to do, double increment, int n, return double, n plus 1. Here we're saying, take the result of n plus 1 and convert it into a double, intentionally. You're in control, and that's the key difference. So why should you care about type systems at all? Because they shape everything about how you write, debug, and optimize your code. Static typing helps prevent subtle logic errors before runtime. Dynamic typing lets you build and iterate faster. Strong typing gives you predictability. Weak typing gives you flexibility. Mastering these concepts lets you choose the right language for the right job, and understand why languages behave the way they do. In the end, whether you're coding in C, Java, or Python, understanding types isn't optional. It's foundational. The more clearly you understand how your language handles data, the fewer bugs, crashes, and weird results you'll face later. Ever wondered why your variable just disappears the moment your function ends? Or why C throws that undefined variable error even when you just declared it somewhere else? We'll cut through the confusion. And by the end of this lesson, you'll understand exactly how C decides where and when your variables actually exist. 1. The core principle. Scope determines visibility. In C, where you declare a variable defines where it can be used. A variable declared inside a function only exists within that function, and only after the line it's declared on. We call this local scope. Think of it like a VIP badge that only grants access inside that one function. Outside of it, that variable doesn't exist. 2. The common pitfall, when a variable goes missing. Let's look at a simple and classic mistake. Main. Example_fn. Printf. %d\n. Example_var. Void example_fn. Int example_var equals 4. Printf. %d\n. Example_var. Inside example_fn, everything works perfectly. You declare example_var, assign it a value of 4, print it, no problem. But the moment main tries to print the same variable, the compiler stops you. Why? Because example_var doesn't exist in main. It only lives inside example_fn. Once that function ends, its variables are gone, erased from memory. This is C's way of keeping your data organized and isolated, avoiding unexpected interference between functions. 3. The fix: declare your own variables in each scope. Here's how we make it valid. Main. Int example_var equals 3. Example_fn. Printf, %d\n, example_var. Void example_fn. Int example_var equals 4. Printf, %d\n, example_var. Now, both functions have their own copies of example_var. When this runs, the output will be 4. 3. Notice how each function prints its own value. No overlap. Even though the variable names match, they are completely independent. This separation prevents bugs and keeps each function's data self-contained. 4. Parameters follow the same rule. Parameters, the variables you pass into a function, also have local scope. For example, void example_fn, int example_param. Printf, %d\n, example_param. Here, example_param exists only inside example_fn. Outside of it, the compiler has no idea what example_param means. So just like local variables, parameters are temporary. They live and die with the function call. 5. Key takeaways: scope made simple. Let's wrap this up with some golden rules you can use right away. Local variables exist only within the function they're declared in. Same-named variables in different functions are completely separate. Parameters behave exactly like local variables. They don't exist outside the function. To share data across functions, you'll need global variables or return values, which we'll explore in the next lesson. Understanding scope isn't just about fixing compiler errors. It's about writing cleaner, safer, and more predictable code. Master this, and you'll avoid one of the most common beginner traps in C programming. Stay tuned, because next we're diving into global variables and how they connect everything across your program. Ever wondered why some variables in your program seem to work everywhere, while others just vanish outside a single function? That's variable scope, and we're diving into one of the most powerful and dangerous features in programming: global variables. By the end, you'll know exactly when to use them, when not to, and how the scope system in C silently controls every piece of data in your program. Let's start simple. What are global variables? In C, a global variable is any variable declared outside of all functions. That means once it's created, it can be accessed by any function within that file. Think of it as a shared container that all your functions can see and use. Here's a quick mental model. Local variables live inside a function, private and temporary. Global variables live outside functions, public and permanent for the program's lifetime. Here's a simple illustration. Int my_global equals 4. Void main. Int example_var equals 3. Printf, %d\n, example_var plus my_global. What happens here? My_global is defined globally, outside the function. Inside main, we define a local variable example_var. When we print the sum, the output is 7, because both variables are accessible in that moment. Even though my_global was never declared inside main, it's visible there because it's global. That's the key. Global variables exist in the program's global scope, accessible from anywhere, anytime. Now let's talk about scope, because that's where most new programmers get confused. In C, scope defines where a variable can be accessed. It's like a boundary line drawn by curly braces. Here's how it works. Any variable declared inside braces exists only inside those braces. Once the code leaves that block, the variable is destroyed. Global variables declared outside all braces belong to the global scope, which means every function's scope is nested inside it. So when you call a function, that function can automatically see all the global variables above it, but not the other way around. Global variables are powerful because they're universally accessible. You can use them to store configuration values, constants, or counters that need to be shared across functions. But here's the catch. Because every function can modify them, global variables can make your code unpredictable. If two functions change the same global variable, debugging becomes a nightmare. So while they're convenient, professional programmers use them sparingly and deliberately, usually for data that genuinely needs to be shared globally. Let's summarize what we've learned. Global variables are declared outside all functions and can be accessed anywhere. Local variables are declared inside functions and vanish when the function ends. The scope of a variable defines where it can be used, controlled by in C. Use global variables carefully. They simplify access but can complicate debugging and maintenance. If you need a variable that's shared between functions but not truly global, consider using function parameters or static variables inside a function. They give you control and clarity without risking global chaos. So next time you're writing a C program, remember, understanding scope isn't just about memorizing syntax. It's about controlling visibility, reducing bugs, and writing cleaner, more reliable code. Ever written a piece of code that should have worked, but didn't? Here's the secret. It's not just what your program says, it's how it runs. We're breaking down one of the most underrated principles in programming: the flow of execution, the hidden sequence that determines exactly how your program comes to life. Every program follows a precise order, a rhythm, if you will. That rhythm is what we call the flow of execution. It starts at the first statement of your main function and moves line by line, top to bottom, just like reading a page. Each instruction is executed in order, unless something interrupts that flow, and that's where functions come in. Think of your program as a road trip. You start at point A, the main function, and drive straight through. But every time your code calls a function, it's like taking an exit ramp. The program temporarily jumps to that new route, the function, executes every statement inside it, and then returns to the exact point it left off. So, calling a function isn't just running extra code, it's redirecting the flow. And that redirection happens countless times, sometimes even within other functions. That's called nested calls. Now, here's a subtle point most beginners miss. When you define a function, your program doesn't run it right away. The definition just tells your program, hey, here's a reusable block of logic, remember where it is. Nothing inside that function executes until it's called. That's why function definitions don't alter the flow. They're like blueprints waiting for a signal to activate. One of the smartest things about C, and most languages, is how it remembers where it came from. Each time a function is called, the program internally keeps a marker, a kind of breadcrumb trail. Once the function finishes, the program follows that marker right back to where it was in the caller function. This mechanism ensures your code always returns to the right place, no matter how deep the nesting goes. Here's a powerful habit straight from the experts. When reading code, don't just scan from top to bottom. Instead, trace the flow. That means, note where each function is defined, but don't read the full body yet. As you encounter a function call, jump to that definition. Follow it through until it returns, and then come back to the next line. That's how professional developers mentally simulate execution, and it's the fastest way to understand any code base. Let's recap. The flow of execution starts in main, and runs line by line. Function definitions don't execute, only function calls do. Each call jumps to a new location, runs, and returns to where it left off. And C keeps perfect track of every stop along the way. Understanding this isn't just academic. It's the foundation of debugging, refactoring, and writing readable code that works exactly the way you expect. If you can see the flow of execution in your head, you can read and write code like an engineer. So next time your program surprises you, ask, where did the flow go? Ever wondered how your code decides what to do next? That split-second decision, whether to run a line, skip it, or branch in a new direction, comes down to one simple idea: Boolean logic. We'll break down how conditional statements and Booleans control program flow, the true decision-making engine behind every algorithm. Up until now, most beginners write programs that execute line by line, predictable, linear, mechanical. But real-world software? It thinks. It reacts. It makes choices. Conditional statements make that possible. They let your program change its behavior based on data, transforming static code into responsive, intelligent systems. If this condition is true, do this. Otherwise, do that. That's the core logic pattern behind everything from login systems to AI decision trees. To control logic, we need a way to represent truth itself. And that's where Booleans come in. A Boolean is the simplest data type imaginable. It can only ever be true or false. Yet with just those two values, you can describe every decision a program ever makes. You can combine Booleans using 3 logical operators. And. Both sides must be true. Or. At least one side must be true. Not. Flips true to false and vice versa. Example in plain English. If it's raining and it's cold, wear a jacket. If it's raining or it's cold, bring an umbrella. If it's not raining, leave it behind. That's all logic is, truth-based decision-making. In languages like Java and C#, Booleans are built right into the language. True and false are literal types. But in C, things are a little different. There's no built-in Boolean type by default, but including the header stbool.h gives you access to Boolean values, true, false, and the type _bool. Under the hood, these are just numbers. 1 represents true, 0 represents false. That's why in C this works. 3 less than 5 true, 1. 3 equals 5 false, 0. Your comparisons always evaluate to a Boolean, a decision point your code can act on. To compare values, we use relational operators, the foundation of all conditional logic. Expression meaning result 3 less than 5. Is 3 less than 5? True. 3 is not equal to 5. Are they not equal? True. 3 equals 5. Are they equal? False. You can even chain comparisons. 3 less than 5 equals 7 evaluates to true, because both comparisons succeed. But be careful. Expressions like 3 less than 5, 2 can be misleading. In C, that actually means is 3 less than 5. True 1, then is 1 greater than 2? False. So, never assume your comparisons chain the way you think they do. Always test and confirm. Here's one of the most infamous bugs in programming history. Confusing assignment with comparison. A single equals sign, equal symbol, assigns a value. A double equals sign, equal sign compares values. If you accidentally write, if x equals 5, instead of, if x equals 5, you're not checking whether x is 5. You're setting x to 5 and then testing if that new value is true. And since 5 is treated as true, the condition always passes. This single typo has caused countless logic errors in production code. Tip: always double-check your conditionals. Many compilers and linters can warn you if they detect this common pitfall. Every decision in a program reduces to Boolean logic. It's not just about syntax, it's about thinking like a computer. Identify what needs to be true or false. Use logical operators to combine those truths. Use conditionals to define what happens next. Once you master that, you don't just write code, you write intelligent flow. Booleans and conditionals form the decision core of every program, from your simplest hello world to the logic that drives modern AI systems. In our next session, we'll build on this by seeing how functions and parameters use these same principles to make your code modular and dynamic. Think in logic. Code with clarity. How does a program decide? Right now, your code probably runs from top to bottom. But to build anything complex, a game, a website, a data science model, your code needs to react. It needs to make choices. This is conditional logic, and you're about to learn its most fundamental tool. The if statement, your first decision. We need a way to check a condition and change the program's behavior. The simplest way to do this is with an if statement. It's a simple if-then promise. If something is true, then we will run a specific piece of code. / award an A grade */ if. Test score greater than or equal to 90. Grade equals A. Let's break this down. This code has one job, award an A grade, but only if the test score is 90 or higher. It has 3 distinct parts. Step 1, the keyword. If test score greater than or equal to 90. First, the keyword if. This is a reserved word in most C-based languages. When your program sees if, it's a signal. It means stop. A decision needs to be made right here. Step 2, the condition, the Boolean expression. Second, the condition. This is always inside parentheses. This is the heart of the decision. Think of test score greater than or equal to 90 as a simple question that can only have one of 2 answers, true or false. The program looks at the value stored in the test score variable and asks, is this value greater than or equal to 90? If the score is 95, the answer is true. If the score is 88, the answer is false. This true/false test is called a Boolean expression, and it's the single most important concept in conditional logic. Step 3, the execution block. Third, the execution block. This is the code inside the curly braces. This is the then part of our if-then statement. This block contains the consequence. It's what happens only if the condition in step 2 was true. Putting it all together, the flow of execution. So, let's watch the complete flow of execution. Scenario A. The condition is true. Our test score is 92. The program hits the if and asks the question, is 92 greater than or equal to 90? The answer is true. Because it's true, the program enters the curly braces. It runs the code grade equals A. The grade variable is now set. Scenario B. The condition is false. Now, our test score is 85. The program hits the if and asks, is 85 greater than or equal to 90? The answer is false. Because it's false, the program skips the entire code block. It jumps directly to the next line after the closing brace. The grade is never assigned, and the program simply moves on. And that's it. You've just controlled the flow of your program. You used a Boolean expression to make a decision. This single concept, the if statement, is the building block for all complex software. Stop writing code that just works. Start writing code that thinks. Your code is making decisions every millisecond. But is it making them efficiently? The most fundamental tool for this is the if/else statement. You might think you know it, but the difference between a junior and a senior developer is knowing how and when to use its different forms. Let's break down the logic. The core, the two-way choice. At its heart, the if/else is a simple fork in the road. It asks one question and has two possible paths. If test score greater than or equal to 90, grade equals A, else grade equals B. Let's translate this. The program asks, is the test score variable 90 or higher? If the answer is true, it executes the first block. Grade becomes A. If the answer is false, the score is 89 or less. The else kicks in. It skips the first block and executes the second. Grade becomes B. It's a binary all-or-nothing decision. One of these two blocks must run. But what about more complex choices? This is where we chain. This is not just running multiple if statements. This is a much cleaner, more efficient ladder of logic. If test score greater than or equal to 90, grade equals A. Else if test score greater than 80, grade equals B. Else grade equals C. Here is the critical takeaway. The code checks these conditions in order, and the moment it finds one that is true, it executes that block and ignores the rest of the entire chain. Let's say the test score is 85. First check, is 85 greater than or equal to 90? False. Move to the next rung. Else if, is 85 greater than 80? True. Execute. The code sets grade to B. Stop. Because it found a true condition, it skips the final else block completely. This is highly efficient. You use chaining for mutually exclusive outcomes. A score can't be both an A and a B. The first one that hits wins. The final else is the catch-all, if nothing above it was true. The gatekeeper, nesting for preconditions. Now, this is what separates a novice from an expert, understanding the crucial difference between chaining and nesting. If update underscore needed equals 1. If test score greater than or equal to 90, grade equals A, else grade equals B. This is not a ladder. This is a gatekeeper. The outer if statement asks a primary question. Is an update even needed? Is update underscore needed true? If the answer is false, the program skips that entire inner block. It doesn't care what the test score is. The logic inside is never even considered. Only if the gatekeeper condition is true does the program enter the nested logic, and then run the second if/else check to determine if the grade is A or B. You use nesting when one condition must be true before you can even ask the next set of questions. So, to build clean, professional logic, basic if/else is for a single binary choice. Chained if/else if is a ladder for multiple, ordered, mutually exclusive outcomes. Nested if is a gatekeeper for checking a precondition before running deeper logic. Understanding this control flow is the first step to writing code that is not just functional, but elegant, efficient, and maintainable. This is one of the most common program crashing bugs. It's called infinite recursion, and it happens when a function calls itself forever. But what if I told you this exact technique, a function calling itself, is also one of the most powerful and elegant tools in all of programming? You just have to learn the one single rule that separates a crash from a clean solution. Let's master it. The recursive leap. Welcome to Recursion. Simply put, Recursion is the process of a function calling itself. Instead of using a for or while loop to iterate, we use the function's own call to create a chain. Look at this code. Our main function calls example_recursive_function and gives it the number 5. /* simple recursion program */ hashtag includes stio.h. Int main void example_recursive_function 5. We start here. Return 0. Void example_recursive_function int counter. Printf %d\n counter. Example_recursive_function counter -1. And here's the problem. Inside the function, it does two things. It prints the current number. It calls itself with that number -1. So 5 prints 5, then calls the function with 4. That call prints 4, and calls the function with 3. Then 2, then 1, then 0. Then -1, -2, and so on. It never stops. Each call eats a small piece of memory, and eventually, the stack overflows. We've built a loop with no exit. The solution, the base case. To fix this, every recursive function must have a base case. Think of the base case as your stop sign. It's the simplest version of the problem that can be solved without calling the function again. Let's add one. We'll tell the function to only call itself if the counter isn't 0. Void example_recursive_function int counter. Printf %d\n counter. Our stop sign. If counter not equals 0, example_recursive_function counter -1. Now let's trace it. It's called with 5. It prints 5. Is 5 not 0? Yes. It calls itself with 4. It's called with 4. It prints 4. Is 4 not 0? Yes. It calls itself with 3. This continues. It's called with 1. It prints 1. Is 1 not 0? Yes. It calls itself with 0. It's called with 0. It prints 0. Is 0 not 0? No. The if statement is false. The function doesn't call itself again. It simply finishes. The entire chain of calls unwinds, and the program exits cleanly. But we're not done. Our code is better, but it's not robust. What happens if the starting number is negative? If we start with -3, it prints -3. Is -3 not 0? Yes. It calls itself with -4. It prints -4. Is -4 not 0? Yes. It calls itself with -5. We're right back to an infinite loop. This is a common pitfall. The fix is to practice defensive programming. Our stop sign isn't specific enough. Let's change the condition from not equal to 0 to greater than 0. Void example_recursive_function int counter. Printf %d\n counter. Our robust stop sign. If counter greater than 0, example_recursive_function counter -1. Now let's check all our inputs. Positive, 5 counts down 5 for 3, 2, 1. On the next call, it gets 0. It prints 0. Is 0 greater than 0? No. It stops. Perfect. Negative, -3, it's called with -3. It prints -3. Is -3 greater than 0? No. It stops immediately. Our function is now safe and handles all inputs sensibly. The recursive formula, the key takeaway. This reveals the two-part structure for all correct recursion. Memorize this. The base case. Ask, is the problem simple enough to solve right now? If yes, solve it and return. This stops the chain. Example. If counter less than or equals 0. The recursive step. If it's not the base case, you must reduce the problem. Make it one step simpler, and call the function with that smaller piece. Example. Counter -1. This distance from the base case is called the problem size. Your recursive step must always shrink the problem size, guaranteeing you will eventually hit the base case. You've just turned a program crashing bug into an elegant and powerful algorithm. Master this pattern of base case and recursive step, and you'll be ready to tackle advanced topics like tree structures, sorting algorithms, and more. Your recursive function looks perfect. It's clean, it's a mirror of the mathematical definition. But when you run it with a large input, your whole program dies. You get the one error every developer fears: Stack Overflow. Why? It's not your logic. It's your memory. We're diving deep into the one concept that explains this: the call stack. Understanding this isn't optional. It's the difference between code that works and code that works reliably. Step 1. Meet the stack LIFO. In C and most modern languages, Your program uses a stack to keep track of its work. The best analogy is a pile of plates. You can only add a new plate to the top. You can only take a plate from the top. You never pull from the middle. This is a LIFO data structure. Last in, first out. In programming, these plates are called stack frames. Step 2. How functions build the stack host. So, what's a stack frame? Every single time you call a function, a new plate, a stack frame, is pushed onto the top of the stack. This frame is a dedicated chunk of memory that stores all the data that function needs to work, its parameters and its local variables. When the function is done, its frame is popped off the top. Its variables are gone, and control goes back to the function below it. This is how your program knows where to return to. Recursion stack attack. This system works perfectly, until we introduce recursion. Let's use the classic Fibonacci sequence as our example. Remember, the sequence is 0, 1, 1, 2, 3, 5, where any number is just the sum of the two preceding it. The Fibonacci sequence. Int Fibonacci, int n, if n equals 0, return 0. Else if n equals 1, return 1. Else return Fibonacci n minus 1 plus Fibonacci n minus 2. Let's translate this code into plain English. Base case 1. If you ask for the 0th number, n equals 0, the answer is 0. We stop. Base case 2. If you ask for the first number, n equals 1, the answer is 1. We stop. Recursive step. For any other number, the function must call itself to find the previous number, n minus 1, and call itself again to find the number before that, n minus 2, then add them. Notice that we have two base cases to stop the recursion, and the function calls itself twice. This is where the heavy burden on memory begins. Step 4. Visualizing the stack overflow. Let's trace what happens when we ask the computer for Fibonacci 4. We call fib4. A frame for fib4 is pushed onto the stack. Fib4 needs fib3. It pauses and calls fib3. A new frame for fib3 is pushed on top. Fib3 needs fib2. It pauses. A new frame for fib2 is pushed on top. Fib2 needs fib1. It pauses. A new frame for fib1 is pushed on top. Great! We hit a base case. Fib1 returns 1 and its frame is popped off. But we're not done. Control returns to fib2. It still needs its second call, fib0. Fib2 calls fib0. A new frame for fib0 is pushed on top. Fib0 returns 0 and is popped. Now fib2 can finally finish and return. Do you see the problem? To solve just fib4, we had this pileup of pending tasks. Now, imagine calling Fibonacci 40. The stack doesn't just grow 40 deep. It grows exponentially wide. You'll have thousands of pending function calls, each with its own stack frame, all waiting for their own children calls to finish. Your program runs out of stack memory long before it finds the answer. That is a stack overflow. The takeaway: recursion is an elegant, powerful tool for thinking. But it is not free. You are trading developer simplicity for computational complexity. Each recursive call is a new function call, consuming real memory on the stack. For problems with a large number of steps, a large problem size, an iterative solution using a simple loop is almost always safer, more memory efficient, and won't crash your program. Understanding the stack isn't just theory. It's the key to writing professional code that doesn't just work in the lab. It scales in the real world. Stop writing the same code over and over. If you need to print hello 10 times, you don't copy-paste printf 10 times. You use a loop. This is iteration, the single most powerful technique for making a computer do work. It's the difference between a calculator and a real program. You'll master the two fundamental loops in C, while and do, while. And more importantly, you'll learn the one critical difference that trips up 90% of beginners. What is iteration? Iteration is just a formal word for looping. It's the process of repeating a set of instructions as long as a certain rule is true. Think of it as a set of a bouncer. As long as the bouncer says go, the code repeats. The moment the bouncer says stop, the loop ends and your program moves on. This rule is called a condition, and it's the key to everything. The workhorse, the while loop. First up is the while loop. The syntax is simple: while, then a condition, in parentheses, and finally a block of code to be executed. The logic: check the condition. The bouncer checks your ID. If false, the condition is not met. The bouncer turns you away. The code block is never run, and the program skips to whatever comes after the loop. If true, the condition is met. You're allowed in. The code block executes, statement by statement. Repeat. After the block finishes, it sends you right back to the bouncer, step 1, to check the condition again. The while loop in action. Let's see a real example. Our goal, print hello 10 times. Hashtag includes stio.h. Int main void. Int count equals 0. We start our counter at 0. While count less than 10. Check, is 0 less than 10? Yes. Printf, hello \n. Run the code. Count equals count plus 1, critical, update the counter. Loop repeats until count is 10. Check, is 10 less than 10? No. Loop terminates. Return 0. Let's trace this. We create a variable count and set it to 0. The loop begins. Check, is count, which is 0, less than 10? Yes. So we run the block, print hello, and this is the most important part. We increment the counter. Count is now 1. The block ends. We go back to the top. Check, is count now 1 less than 10? Yes. We print and count becomes 2. This repeats, finally count is 9. Check, is 9 less than 10? Yes. We print and count becomes 10. Back to the top. Check, is count now 10 less than 10? No. The condition is false. The loop terminates. We've printed hello exactly 10 times. The 2 while loop traps. Pay attention. There are 2 traps here. The infinite loop. What if we forgot the count equals count plus 1 line? Count would always be 0. The condition 0 less than 10 would always be true. The program would print hello forever and crash. You must change something inside the loop that affects the condition. The 0 execution case. What if we had set count equals 11 from the start? The loop would check. Is 11 less than 10? No. The code inside the brackets would never run. Not even once. Remember, the while loop is a pretest loop. It checks the condition before it ever runs. The at least once loop, do while. But what if you need your code to run at least one time, no matter what? For that, we use the do while loop. Think of it as the act first, ask permission later loop. Look at the syntax. The do keyword comes first, then the code block. The while condition is at the end, followed by a semicolon. The logic is flipped. Run the block. It executes all the code inside the curly braces first. Check the condition. Then it checks the condition at the end. If true, it goes back to the do and runs the block again. If false, the loop terminates. The do, while loop in action. Here's the same hello program using do, while. Hashtag includes stio.h. Int main void. Int count equals 0. Do. Printf, hello \n. Count equals count plus 1. While count less than 10. Condition is checked at the yendi. Return 0. In this specific case, the output is identical. It prints hello 10 times. But let's use our trap case. What if we set count equals 11? Do. The block runs immediately. It prints hello, and count becomes 12. While, now it checks the condition. Is 12 less than 10? No. The loop terminates. The result? It printed hello exactly once. Compare that to the while loop, which printed 0 times. This is a post-test loop. The final showdown, while versus do while. This is the only thing you need to remember. While pretest checks before running. Can run 0 or more times. Use this 90% of the time. Do, while post-test checks after running. Will always run 1 or more times. Use this only when you must execute the code at least once, like getting user input before you can check if it's valid. And that's it. You now understand iteration. You know when to use a while loop and when to use a do while loop. Get this right, and you've mastered a core pillar of programming. Next time, we'll look at the for loop, a cleaner, more powerful way to handle loops with counters. Ever write a recursive function that looks elegant, but runs like molasses? Or worse, crashes your program with a Stack Overflow? That's the classic optimization trap. We're replacing that slow, memory-hungry approach with its lightning-fast, efficient cousin, iteration. Why is iteration so much better for performance? Speed. It's often faster because the program doesn't have to manage the call stack, pushing and popping function calls. Memory. It uses way less memory. No stack overhead means your program stays lean. This is the kind of optimization that separates beginners from pros. The iterative buildup, Fibonacci. Let's look at a perfect example, an iterative Fibonacci sequence generator. Instead of working backwards from the number we want like recursion, this builds forwards from the beginning. Iterative Fibonacci. Int Fibonacci, int n. Int previous equals 0, int cur equals 1, int next, int count equals 2, while count less than equals n. Next equals previous plus cur, previous equals cur, cur equals next, count equals count plus 1, return cur. Deconstructing the code. This looks simple, but its efficiency is in the logic. Let's trace it. Initialize base cases. We start by setting previous to 0 and cur, current, to 1. These are the first two numbers in the sequence. Start the count. We set count to 2. Why? Because we've already handled the first two numbers, at index 0 and 1. Launch the engine. The while loop runs as long as our count is less than or equal to n, the target number we're trying to find. Calculate next. Inside the loop, next is calculated by adding the two previous numbers, previous plus cur. This is the core Fibonacci logic. Shift the window. This is the key. We set previous equals cur. The old current number becomes the new previous number. We set cur equals next. The newly calculated next value becomes the new current number. Iterate. We add 1 to count and the loop repeats, shifting the window up the sequence one step at a time. Return. When the loop finishes, cur holds the Fibonacci number at position n. No recursive calls. No stack bloat. Just pure, efficient bottom-up calculation. Pro strategy. Incremental development. Now let's use this iterative power for a classic computing task, generating mathematical tables. But we're not just going to dump 30 lines of code. We're going to build it using a professional strategy, incremental development. This means you build and test in small, manageable pieces. It saves hours of debugging. Step 1, the skeleton first. We build the absolute minimum, a main function that calls our create_tables function. Void main, create_tables. Void create_tables, void. We'll build here. Printf, function called \n. A simple test. We compile and run. Does it print function called? Yes. The plumbing works. Step 2, the loop scaffold. Next, let's build the loop mechanics without the complex math. We just want to see if we can loop 9 times. Void create_tables, void. Int count, count equals 1, while count less than 10. Printf, placeholder \n. Count equals count plus 1. Don't forget this. We run it. Does it print placeholder 9 times, for numbers 1 through 9? Yes. The loop structure is solid. Step 3. The real logic. Now we add the real calculation. We'll replace our placeholder with a log table. Void create_tables, void. Int count, count equals 1, while count less than 10, the new logic. Double. L equals log count. Printf, %d\t%f\n, count L. Count equals count plus 1. Let's break down that new part. Double L equals log count. We declare a high-precision number, double, called L and set it to the natural logarithm of our count. Printf, %d\t%f\n, count L. This is formatted printing. %d says print an integer here, our count. \t inserts a tab for clean columns. %f says print a floating point decimal. Number here, our log value L. \n moves to a new line. And the result? A perfectly formatted, 9-line table of logarithms. We built it incrementally, tested at each stage, and used a memory-efficient while loop. That's the power of iteration. You're not just writing code that works, you're engineering code that performs. Are you still using while loops for simple counting? There's a cleaner, more powerful, and more professional way to iterate in C. If you want to control your loops and not just let them run, you need to master the for loop. It's the single most common loop you'll see in professional C code, and we're breaking it down into 3 simple parts. This structure looks technical, but it's just a simple recipe. Think of it as setup, check, and update. Let's look at this real-world example. Hashtag includes stio.h. Int main void. Int n. The for loop. For n equals 0, n less than 10, n plus equals 1. Printf, %dn. This code will print numbers to the screen. Let's trace the loop's 3-step logic. Step 1. The initialization. The first part, n equals 0, is the initialization. This statement runs exactly once at the very beginning. We're creating a counter, n, and setting its starting value to 0. Step 2, the termination condition. The second part, n less than 10, is the termination condition. This is the gatekeeper. Before every single loop, the program checks this condition. It asks a simple question. Is n currently less than 10? If the answer is true, the code inside the curly braces runs. If it's false, the loop stops completely, and the program moves on. Step 3, the increment. The third part, n plus equals 1, is the increment. This statement runs after each pass through the loop. So, after we run our printf statement, the program executes this increment. By the way, n plus equals 1 is just a professional shorthand. It means take the current value of n, add 1 to it, and assign the result back to n. It's the engine that drives the loop forward. Tracing the execution. So let's trace this. 1. Initialize. N is set to 0. 2. Check. Is 0 less than 10? Yes. So we enter the loop. 3. Run body. The program prints the current value of n, which is 0. 4. Increment. N is updated to 1. The first pass is complete. Now we start the second pass. We skip the initialization. That's done. 1. Check. Is 1 less than 10? Yes. 2. Run body. It prints 1. 3. Increment. N becomes 2. This process repeats. It prints 8, increments to 9. It checks. Is 9 less than 10? Yes. It prints 9. It increments. N is now 10. Now the final check. Is 10 less than 10? No. The condition is finally false. The loop terminates. We never run the printf for the number 10. The program exits the loop. And that is the for loop. Initialize once. Check the condition. Run the code. Increment the counter. Go back to step 2. It's a clean, dense, and efficient structure that puts all your loop control in one place. This is a fundamental pattern for any serious programmer. You've just upgraded your C programming toolkit. Use this to write cleaner, more readable code.